It's great to be here. I was a graduate student at Michigan and heard about these lectures, but I'm ashamed, I really am ashamed to say I've never been to one of these. And so this is really exciting on two fronts. I guess I want to start this talk by telling you what it's not about. I asked my 8-year-old sister what she thought this all meant, and she said, well, she had no idea. So I asked a few other people, and what it's not about is quantum drives in Star Trek. It's also not about nuclear physics and nuclear bombs. Us atomic physicists, I'm not alone in that whenever someone sees the word atomic, they think of bombs. And of course, nuclear bombs involve atoms, but they involve the nucleus of the atom mostly and not the whole atom. So I like to say that us atomic physicists we're a little more inclusive about the word atomic. Anyways, but what this talk is about is really an exciting time that we are in right now, where quantum mechanics, which was really formulated almost 100 years ago in the sort of 1920s, and the almost century since then that's been tested and verified in wonderful experiments and of these physical systems of atoms and on the atomic scale that are now becoming real technologies. So we're in this transition phase where we can use atoms, we can use quantum mechanics to do practical things in our everyday life. And so for this talk, I'm going to make it into a Saturday morning business lecture for part of the beginning of it, but then certainly Saturday morning physics to talk about some of the quantum sensors and technologies that we're developing at Rydberg Technologies that's grown out of this work that was done at Michigan and other places, and also give you an overview about this quantum technology industry that's really going on around the world now. Let me just start by give you a profile of Rydberg Technologies. So I defended my PhD in 2015. I worked with Professor Georg Reithel over here in the physics department. And we started doing measurements with atoms and these Rydberg atoms, and basically showed that we could measure electric fields with these atoms. And I did my PhD and completed my thesis, and as many graduate students, the situation many graduate students are in, where they kind of thinking about what to do, my ideas were all over the place. So whether to do a postdoc or go into industry, go into finance, I had no idea. So I did some postdoc searches, I did some interviews, and a couple months after my defense, an announcement came out from the federal government to develop a technology based off of some of the measurements we had done. And so it was one of these, sort of what I felt kind of just sort of fell in my lap, and it was basically saying, start a company and make something from what you did. And what a wonderful place to be in. I feel very fortunate to do that. So I approached my advisor at the time, Georg, and we founded Rydberg Technologies to do just that. And so now we're about 2.5 years old. We have our main offices and facilities in Michigan and over at MIHQ on Wagner Road and at Spark downtown. And we're mostly federal and state of Michigan funded and some private investment to develop these technologies based off of this research. And we continue to have really active collaborations, both with the University of Michigan and with the National Institute of Standards and Technology on developing our technologies. So what is quantum technologies? So they're technologies based on the laws of quantum mechanics, which govern the physics on an atomic scale. And it's going to lead to a wave of new technologies that will create many new businesses and help solve many of today's global challenges. This is from the EU and the European Union's roadmap and manifesto for quantum technologies. And there's a lot of support around the world for this. Just as some examples, in 2015, the UK established this roadmap and really a national initiative to bring these technologies to bear. And they invested $270 million to basically create the infrastructure, go into academia, industry, and government to support this transition from lab to the marketplace. Similarly, Europe followed up in 2018 and 2016 rather, with their Quantum Manifesto, and are investing up to €1 billion this coming year to bring these technologies forward. And in the US, we don't have a big roadmap, but there are initiatives on sort of the smaller scales, and particularly the DARPA Quasar program, which we were a tail end of, and these other agencies, including NIST. And why is it that they are investing this money? Well, there's really going to be a big economic impact. There's about $2.4 billion were invested by governments in 2015 across the world, including China, European Union, UK, the US, because they're really expected to have a really profound impact on many markets that we know today. So the telecommunications, defense, aerospace, and we already see a lot of industry investment in quantum computing, for example. We know well-known companies, Microsoft, Google. Google just headline just a few months ago, Google just revealed how they'll build quantum computers. Microsoft has a full stack solution to quantum computing. So these are real investments that are happening today. IonQ is a smaller startup company founded by a former Chris Monroe, who used to actually be a physics professor here at Michigan, to develop quantum computers based off of ions. And on the sensing side, and I'll get to this later, there's also growing industries of companies that are developing quantum technologies to measure fields and measure things rather than compute. And even big companies like Honeywell, Northrop Grumman have research groups doing this. And one thing these all have in common, and what needs to happen today, I want to take this opportunity to emphasize this, is that it really is that industry needs to take the lead to bring these quantum technologies forward. The University of Michigan or other universities, academia is not going to make the sensor that's installed in planes for navigation. The industry needs to take this leap, but this is an industry that there's a transition period where we need to get these quantum technologies actually developed. And the timeline for this is not 6 months like you would with an app. It's more of several years to get these things into to a point where you can sell them on the market. And so there's really needs to be a continued partnership between industry taking this lead to develop and bring these technologies to market. Academia really needs to continue to do what they do best, is continue to advance the basic science and applied research, but also to engage and teach the students to be able to work in this field of quantum mechanics and quantum engineering, because at the end, we live in a classical world. You need to be able to push a button and have something do something, and that something needs to be quantum mechanical. So doing that and training a workforce to be able to solve those problems is important. And of course, government needs to be provided resources and to support these endeavors. And I just want to say here, this is straight out of the UK roadmap, that academia must look to provide the same level of support to entrepreneurial individuals trying to exploit the technology as it does to individuals involved in exploratory fundamental research. And I think this is just wonderful, and we need to do more of this, and this is something that really motivates the type of efforts that we have on Rydberg Technologies and other spin-offs from universities. So what are quantum technologies? Generally, as was mentioned in the introduction, you can divide it up into two camps. There's quantum information, which is really systems that involve the processing and transfer of information. And then there's quantum sensing, which is concerned with basically how to measure physical quantities in this world. And the two, of course, quantum computing could lead to being able to solve currently intractable computational problems, as well as simulate very complex systems. And of course, encryption and secure communication is a very big topic, and focus in what quantum information and quantum computing can provide. In quantum sensing, we're talking about improved navigation and timekeeping, so the atomic clock, and the existence of GPS, geolocation. All of these things, electromagnetic sensing and imaging, are expected to be significantly impacted by these new technologies. And due to this, the timeline for these technologies is quite a wide range. So quantum computers aren't anticipated for another 20, 25 years. There's really needs a lot of development to go into these technologies. And the quantum sensing and these sensors to measure physical properties have a much shorter timeline, which make it much more realistic to start a company or develop these technologies and actually think about where you can, who might need them, where you might sell them. So the quantum sensors have potentially one of the shortest time horizons to actually bring these technologies to market, and also potentially the biggest technological payoff. So quantum sensors, a lot of the components and technological hardware that goes into these quantum sensors may also be very relevant to quantum computers and quantum technologies for quantum information. So quantum sensors, to give a quick outline, basically the key is to measure physical properties with each of these, with different sensors. So each of these sensors exploits a different type of aspect of quantum mechanics to make these measurements, the most famous of which, I already mentioned, atomic clocks to measure time. We have a picture of the NIST fountain clock, which is our time standard now. And this has been under development quite a while until there's actual commercially available atomic clocks today. They're not quite as sensitive as we'd like, but they're sensitive enough for GPS and a lot of the synchronization that's needed for these things today. Acceleration, atoms in these quantum systems can be very sensitive to inertial changes or acceleration, which can be used for advanced navigation. A subset of that is the very precise measurements of gravity or changes in gravity. So here you see a map of the Earth and the gravitational changes around the Earth. And atomic gravitometers are developed now and available, which hold a lot of promise to measure, for example, underground and do imaging below the Earth's surface. So you imagine oil drilling and geophysics. And then there's the field sensors, so magnetic fields. Magnetometers based off of the response of the atom to magnetic fields are also coming to market and doing things like geomapping, so measuring the magnetic field around the Earth, and measuring small in the medical field, measuring magnetic variations from heartbeats in children, in fetuses. And then there's electric fields. And field measurements are where Rydberg Technologies is focused on, and particularly with electric fields. And this is, in the context of all these technologies, we're a very kind of new technology. There aren't, we're in the process of developing these types of technologies right now, so we're excited and are looking forward to doing this right now. And so what are these electric fields that we measure? So one of the largest, one of the most common places and where we're more interested in is in radio waves. So radio waves are everywhere. We don't see them, but they are extremely important. We use them for communications, radio, FM, XM, radar, cellular, Wi-Fi, Bluetooth, and it concerns the electromagnetic spectrum at frequencies anywhere from about a kilohertz, which are kilometer-long wavelengths of radiation, to hundreds of gigahertz, which can be wavelengths of about a millimeter. And it's really, it's impressive to think about how common these are. It's really everywhere. We are all emitting this radiation now from our cell phones in our pockets. There's Wi-Fi signals flying around everywhere. And the bands are extremely crowded, so there's so much information flow that the governments have to regulate what frequencies can be used for certain applications. This is a map of the different frequency allocations for specific applications, and each of these boxes shows what can be done with certain frequencies. You see it's getting, it's extremely crowded, and we commonly use lower frequencies, but there's also a push to go to higher frequencies so that for basically higher data transfer and communication. So if, one thing maybe some of us have experienced when your cell phone drops out, or when you try to go to Michigan Stadium for a football game and you can't call anyone, well, that's simply because the bandwidth is too low and everyone's trying to make calls. And so going to higher and higher frequencies is something that the federal government and everyone is trying to do. So of course, the key to this, to using these, is you need to be able to both emit and you need to receive this radiation. And this is technology that's been around for a while. It's just basically antennas. You need an antenna to transmit and receive this type of radiation. And basically, this is a little graphic you may have seen. This is an electromagnetic wave that's propagating, and it has an electric field component, and it's impinging on a little dipole antenna, which is a metal structure. And you can see as the electric field passes by this metallic conductor, the charges oscillate back and forth inside the metal conductor and cause a current from which you can get a signal output. And that's on the receiving end, and of course, if you want to use it to emit, you just run a current, oscillating current through the antenna, and you emit the electromagnetic wave. And this basic technology, you know, we've got antennas sitting around here. Here's one. This is exactly what a dipole antenna looks like. And basically, this technology hasn't changed since its invention. So here's the first horn antenna in 1938 to the 1940s and World War II, with radar came to prominence. There's a large, building-high antenna. Of course, car antennas, the advent of FM radio, and to cell phones. This is a picture of an iPhone 4 antenna system. You can see the antenna is wrapped around the iPhone, and all of these communication technologies have antennas in them. In 2020, it's predicted that with this Internet of Things, we're all synced up and talking to each other, that there's going to be over 50 billion devices that are all connected to the internet and talking to one another. And what's amazing is that this basic principle has held for this long. So we rely on antenna technology and this conversion of electromagnetic radiation to current through a metal structure, and for all of these things. Uh-oh. And because of that, there are limitations that these antennas have. So technology hasn't changed, and some of the problems are listed here. Basically, the antenna is limited in basically the number of frequencies a single antenna can measure. So you need very large antennas, for example, to measure very large wavelength radiation. So if you have 10 megahertz radiation, you've got a meters long wavelength. You need a bicone antenna that could be this big. This antenna right here measures 82 megahertz radiation. It's, the wavelength of that is 3 meters. So you've got about 1.5 meters long dipole antenna here. So of course you can imagine if you want to measure that field in a compartment, say, you're not going to be able to do that with an antenna. They also require calibration, so it's a metal structure. So as soon as you bend the antenna a little bit, it's not going to work the same way. And so it's really sensitive to changes, not only in the material, but it's also, to some extent, pretty delicate in how it works. And in order for it to work consistently the same way, they need to be calibrated. Finally, there's also a problem with, because it's inducing a current in these metal structures, it doesn't take, when you apply very strong electromagnetic fields on it, and strong RF, you can actually heat up and damage the antenna. In addition, they're susceptible to interference. So if you're trying to measure the radiation from an antenna with an antenna, they can couple and interfere with each other in the process. And this actually happens with your cell phones. If there's a problem with the iPhone 4 where if you held it in a certain place, you could actually decouple or change the response of the antenna in the iPhone, and it actually changed how strong your signal was in your cell service. So there's these issues that are still carried through, and they're linked to the limitations of antenna technology. So what we're doing is we're essentially developing the atomic clock for electric fields. We want something that's reliable. Atoms never change. An atom is an atom here as it is on the moon. And they're just to perform better, reliable measurements of electric fields to replace this receiving antenna technology. So how do we do that? So I'm going to switch gears to some atomic physics here. And so atoms, we know there's, as the Greeks named atomos for the unbreakable constituents of ordinary matter. Of course, we know they're breakable, hence nuclear physics and nuclear bombs. But generally, they're unbreakable in our everyday life. And atoms are quantized, right? So the energy states of the electron orbiting the charged nucleus can only exist in discrete energy states. And with that, it emits and absorbs light at discrete frequencies when it makes a transition from one quantum state to the next. And so these atoms, what we can do is, of course, you can't see. One way that we actually look at atoms and see atoms is to look at these transitions. So if we shine light at the right frequency, we can actually see where that transition is. So we get a picture of the atomic structure. So here's a little demo here that's give you some intuition for this. And so basically this is a light filament, just a filament light bulb. And there's a diffraction grating which shows the components of the frequency in this light. And this light is propagating into this diffraction grating, and you see all of the frequencies, and the frequencies correspond to each of these colors. So you've got the higher frequencies in the blue, and you get lower frequencies towards the red. And you have these glasses they're called glass blower glasses that basically have sodium in them, so the sodium atoms. And the sodium atoms have an energy transition at a yellow frequency. So if you put these glasses in front of the camera, you can see that where the yellow is, the yellow vertical stripe up and down, there's a gap, and it turns black. So what's happening here is the light that's passing through these glasses is getting scattered and doesn't get past the glasses because of the sodium atoms inside of the glasses. And so this is basically to illustrate that using a light source like this, you can actually see the transition in the atoms that are in this material. And this is sort of to give you some physical intuition on how we can look and see what atoms are doing with light. And so the same thing that we can do with atoms like this, and we can turn this. Actually, I'll leave that on for now. So the atoms that we're concerned with, what I'm talking about here, you typically get a sense for the size of atoms, so how big an atom is. Basically, to get some sense of scale, you could imagine, and this is from a very famous lecture, some of you might know this, but if you consider an atom an apple, if you blow that apple up to be the size of the Earth, an atom is as big as the original apple is to that magnified apple. And so that's the size sort of scale that you get for regular atoms that we talk about. But the atoms that we deal with for our technologies are called Rydberg atoms. And what Rydberg atoms are is that if you take one electron from a normal atom and you excite it to a very high-lying orbit, so it's very far from the atomic core, you get a very large atom. So if you take that same analogy and you take an apple, the Rydberg atom would basically extend out to Michigan Stadium from here. So it's a giant atom. And what that is, and in reality, they can be as large as about 1/100th of a human hair. So think about that. This is a quantum mechanical object atom that's almost macroscopic in size. There's viruses that are that big. And so it's a very interesting system for a lot of reasons. There's a lot of interesting research going on. And for us, one aspect of this is that this electron that's flying around the atomic core is very sensitive to electric fields. So it's basically almost a free charge, not quite, but almost a free charge that can react to its environment if an electric field or a magnetic field comes by. And so basically the effects on these atoms, both the electric fields, it exhibits what's so-called AC and DC Stark shifts, and for magnetic fields, Zeeman and diagnetic effects. And we can see these effects the same way. So we can basically see the atomic structure using light, and from that atomic structure, we can then, and how that changes in the field, we can then get information on that field. And so in this next slide, of course, this is to explain this. This is now a true sort of quantum mechanical description of these Rydberg atoms in fields. So if you look at this is on the very far left side. If you just look vertically, this axis is basically a change in the light frequency of a laser. So that's the equivalent of going from left to right on this sort of analogous system. And if you go up and down, you see right here there's a resonance. So at this point, that would be the equivalent of me, of basically seeing where that resonance is. So at that frequency, we are hitting that resonance in the sodium atoms. In this case, we're hitting a resonance in this case, it's a rubidium atom. Doesn't matter too much. Now, if you look at that resonance and you increase and you apply an RF electric field, an RF field, you see that the atomic structure is changing. So as you increase the strength of an RF field on these atoms, the atoms are interacting with that field, and their structure changes. And we can, and all of these are different quantum states of the atom in this field. And if you take a single point in this map and you actually plot the quantum mechanical electronic probability, so basically where the electron can be around this atom, you get these plots that look like this. Basically, if you have an electric field coming in this way, your electron can be anywhere located in this probability distribution. And what's remarkable is that this wave function changes. This probability distribution is unique to this point, and throughout this whole map, at each step, the atom looks a certain way. And a large part of sort of the development and moving towards being able to use these atoms and these quantum systems to measure fields is to be able to model this. So we're not only looking at what an atom is, but we're looking at the interaction between an atom and its external field. And that's really complex. You just look at the structure. You can't make this up. And you rely on these quantum mechanical laws and develop basically these models to be able to model the atom very precisely. And these models are exact. There's no free parameters. It doesn't matter if you look at it with brighter laser light or lower laser light. The atomic structure doesn't change. And so this, it's playing already, shows you basically, this is a nice movie from actually a former colleague graduate student that's in the audience. This shows, I'm going to start it again. Well, it apparently just wants to play. So if you look at the very beginning, if I click it now, this is basically an atomic spectrum. This is an optical signal, so we're looking at the transmission of light through this atomic sample. And on top is the corresponding electric field. So you see as this field increases of this RF signal, the optical spectra change. So this is, you can imagine if you're looking at the atom, which is that main picture, and you have some antenna horn or some field propagating, and you turn up that field, this is how the atom changes as you turn up that field. And we can use this to measure the electric fields. So that's how that's fundamentally how it works, how we measure. But in practice, how do we actually do this? So atoms are, everywhere, but we need a very controlled sample. We're not talking about atoms in glass. We use basically atoms in small little compartments as our sensors. So now we're talking about what's the practical implementation of this. And so if we look over here, we can see in this projector, I have a couple typical what are called vapor cells. So these are glass compartments that they're basically evacuated and contain basically an atomic vapor inside. And we can make these, all kinds of different sizes. Here's one that's a very small little vapor cell. And you can already see that their size compared to sort of standard antennas are very small. And so this is a little sensing element. We have our atoms in there, and we use the same spectroscopic technique to shine light through these cells to see what the atoms are doing. And so a typical operation of one of these sensors is you have some unknown field that you want to measure. You have these atoms in your little sensing element, vapor cell, that you put inside the field as your sensor. And when the field interacts with these atoms, the quantum states of these atoms change. And so in order to see what that change is, we look with our laser and we see what the atomic structure does, and we get spectra, and depending on what that looks like, because we know the model and we know what the atom should look like in certain fields, we can pull out the information about the field. And something I want to point out is that these quantum states, this idea that we've excited electrons to these high-lying states as Rydberg atoms, those states exist whether the electron makes it there yet or not. And this is sometimes a counterintuitive at first, but quantum states exist. And then when you make a measurement, you get some artifact of that. You can see where those states are. But if you have an atom and it's interacting with a field, its quantum states, like you saw in the previous map, are there, and then you look to see how that atom has been modified with the light. And so we make our measurement with the light, and that measurement tells us how the atom has changed, and from that spectrum and that output, we can then get the information on the field. And so what we have is basically we have these little atomic sensors that can measure measure these electric fields, and because they're atoms, they don't change. They're not metallic, so they remain atoms. They don't change if you can't really bend an atom. And so they're very reliable, and you don't need to calibrate them. What you measure with an atom is what you measure with an atom. They're very broadband, so this Rydberg atoms are sensitive to electric fields from megahertz all the way up to gigahertz, so a range that spans a majority of the radio spectrum. Instead of requiring many different antennas of different sizes, you can use a single one of these little atomic sensors to measure what you would otherwise need many antennas to measure. Small size, you can actually get very sub-wavelength imaging. So if you consider the electromagnetic field from this antenna, I said it's 3 meters long. Well, now instead of using an antenna that's half that big, you can measure the field with a millimeter size sensor, and you can get, you can basically measure the entire wavelength and below the wavelength and resolution. They're very precise because we can measure the atomic parameters in these quantum systems to within sort of calculation uncertainties really of 0.1. Very sensitive, so you can measure very weak fields as well as very strong fields. So another advantage of these sensors is that because there's no metal, you can't heat it the same way. You don't, there isn't any heating of the metal, and basically they're damage-free up to a very strong field. So you can do things with these sensors that you couldn't do otherwise. And so next I want to tell you some about the applications that we actually demonstrate and do with these sensors. And one of them is, as I already mentioned, that a single sensing element can measure a wide range of frequencies. And here I'm just sort of highlighting the portion of the entire radio spectrum that these single sensors are sensitive to and can measure. And one with regards to this push towards higher frequencies and faster data transfer, really these next generation 5G networks, as they say, you need to be able to measure those fields, and there's actually no standards now. So atomic standards for time. The standards for electric fields are antennas. And there are currently no millimeter wave standards yet. And so something that we did early on, back when I was in Michigan with NIST, is to make the first millimeter wave standard measurements, in this case up to 100 gigahertz with these atomic sensors. So it allows for these measurements. And of course, millimeter waves, if you can sense these, there's a lot of other applications you can think about. For example, the millimeter wave scanners at airports operate at these types of frequencies. So you could imagine new sensors for advanced imaging and similar applications. Another application, something that's of real interest in RF engineering and antenna design and radar, is to make antennas that work just the way you want. So you want to know, for example, sometimes that an antenna radiates in a particular direction. You don't want your radar going everywhere, but you want it focused somewhere where the plane's flying overhead. And so to do that, you need to design your antenna just right. And it's really hard. One thing people want to do is basically measure the antenna, the field that's right in front of an antenna. And that's really hard to do with another antenna of the same size. You basically have to put two antennae side by side. And so here what we did was we actually took this very antenna here. This is a little horn antenna. I'll just hold it up. It's right here. And use an atomic sensor to basically map the electric field profile in space in front of this antenna. And what you see is the antenna is about an inch long and a little less than an inch high. And we take our about 2.5 millimeter size sensor and we scan it around in front of the antenna. And what we can recover is this nice electric field profile. Here the dotted line shows the outline looking forward of the face of the antenna. And basically the color scale, the darker color indicates a stronger electric field, and the lighter white is a weaker electric field, and we see this nice field distribution in front of the antenna with lambda over 10 wavelength resolution, which would otherwise be impossible. And the nice thing is not only that we get this nice experimental map, which is often now simulated, people just need to simulate this, you can actually get experimental data and measure these antenna profiles, and it's also interference-free. Because these are little metal-free cells, you don't have another conductor or metal element that's interfering with the process. It's a much cleaner measurement. And finally, this is, we also, third demonstration, we measured very strong fields. So there's no picture of this on the slides, but basically measure the field from an antenna that's amplified to very high power, and we can measure kilovolt per meter fields and higher, which is something antennas struggle to do. They basically, if you want an antenna to measure the field very carefully, typical antennas won't operate well above 100 or so volts per meter for measurements. And so we have a sensor here that can measure fields that would otherwise you would not be able to measure easily. For this, there's really a lot of room for applications here. I've just listed some things just to highlight where these types of sensors could be used. Antenna atomic standards, so we work closely with some collaborators at NIST who are interested in using these and making these systems so that there's an atomic standard for electric fields instead of antennas. Calibration and characterization, here you see a picture of basically an anechoic chamber. This is basically a soundproof room, but for RF and microwave, so they don't bounce off the walls. And there's an antenna right there at the center that we want to do an antenna characterization of. And you see here we've got two antenna, but you can imagine using basically a small atomic sensor for these types of applications instead of an antenna. Circuit design, you have RF power circuitry being developed for smaller, more compact devices. You want to be able to measure the fields that's being radiated from these circuits so they don't interfere. So something you don't want is you don't want to bring your cell phone into the kitchen and have it disrupt your microwave from its emissions, or you don't want your brake in your car to interfere with your GPS. So it's really important to be able to measure fields and check these levels, and our sensors can measure these small circuits on very small spatial scales. And of course there's a lot of sensing in RF and microwave and millimeter wave, and in remote sensing, in astronomy and planetary science. In security, I've already mentioned, imaging millimeter waves can see through your clothes and on your skin to check for weapons and such, and in biomedical imaging too. So the applications are really pretty wide, and as our development continues with these types of sensors, we hope that more applications will come out too. So I'm going to tell you briefly in the last couple slides about two other quantum sensing technologies that we've sort of developed since over the last year or so, which are related. So one is to use the same principle of looking at how atoms change inside of electric fields to measure electric fields inside of plasmas. So basically plasmas are often considered so-called the fourth state of matter, but they're very relevant in astrophysics, physical phenomena, but also in you find them in microfabrication process in the silicon industry, microelectronic industry, where plasmas are used to etch down materials. And basically the electric fields inside of these plasmas, which are a collection of charges, if you know those fields, you can learn a lot about the plasma and control the plasma. So being able to measure electric fields in these systems is often of interest. And so we basically developed a method by you can inject these atoms inside of a plasma, and you can use the same basic principle looking at the quantum states and how they change inside the plasma with an optical beam to then get information on the electric field. So here, some pictures of spectra. Here you see a resonance, an atomic resonance, when there's no plasma. And you see that if the atom is placed inside the plasma, you see how the atomic structure changes. And a big part of these quantum technologies that we're developing is understanding how that atom changes and how to model it quantum mechanically. And this is a very nice place where we basically ask the question, well, we want to measure plasmas. This is our application. Let's go back to the lab and try to understand how the atoms respond to these situations and model that quantum mechanically. So the link between sort of what used to be basic research in the lab, understanding what atoms do, and actually solving a problem for someone is much more immediate, which is a very exciting place to be for sort of these quantum technologies and the development. And I have here too that this really is, I think, a record. We actually managed to measure the weakest electric fields in a plasma to date using this same technique. And then finally, Rydberg atoms, not only are they sensitive to electric fields, but they're particularly sensitive in strong magnetic fields. Basically, they can measure fields over milligauss to many Tesla. So MRIs typically work at a few Tesla. And they're also these atoms respond very quickly. We can get a very fast readout for changes of the magnetic field that these sensors are in. And of course, it's still metal-free and interference-free. So being able to use the same principle to measure strong magnetic fields is something we did a lot of work on and are pushing forward. And this type of high magnetic field quantum sensor you could think about using for calibrating superconducting magnets or strong magnetic fields, and potentially also to map out the magnetic fields in MRIs and MRI and magnets in general. So with that, I think I'll conclude. So in summary, basically told you a little bit about Rydberg atom electric field sensors primarily, and how they really are an antenna replacement. We really hope these things to be an antenna replacement that can basically have applications in RF sensing, measurement. Two new types of quantum technologies I mentioned, plasma diagnostics and high magnetic field sensors. Just want to say that this area of really pushing forward the capabilities of these Rydberg atom quantum sensors, it's a very fruitful area to say, where do you want to measure? How can we go back and see, okay, let's understand what the atom is doing and then use that to be able to tell you and perform that measurement better. And that's we're doing a lot of things like pushing how to detect very sensitively, very low levels of RF noise and thermal fields, basically getting not only sitting in the lab, and as a graduate student, you try to write papers and you write abstract about applications. We actually get to go out and we talk to people and say, what do you need? And then we go back to the lab and we can write our abstract and say, this is what's needed, and we're going to make this, for you. And so it's a nice transition from a graduate student, something that I appreciate in what we do now. And then finally, I want to make some general remarks on this quantum technologies industry. It's really the case that there's a lot of investment going on around the world in these types of technologies. And it's really important that the United States and even here in Michigan that we get on board. Quantum technologies are going to become a big part of this world. And you see in these and it's happening around us. So what that's really going to take is industry needs to, of course, do this. They need to make the technologies, but the support of academia is to help transition these technologies from the lab to the marketplace is also really important, and basically also to train the so-called as they say, quantum workforce. It sounds pretty cool. I don't know if you put that on your resume. But it's really true that we need to prepare, so we need to solve these challenges and be able to make these technologies. And academia has an important role in that. And finally, it's going to lead to hopefully really great societal as well as intellectual and economic benefits. So it's a very fruitful area for bringing quantum mechanics and developing new technologies rooted in some very basic physics for practical applications. And so on that note, thank you for your time, and I'll leave it at that.